All right, welcome to the second half of our discussion of titration and titration stoichiometry. We are going to put what we know about the ideas of equivalence point, endpoint, molarity, and stoichiometry all together in this given example here. So let's dive right in. So I am told that a 1.0 milliliter sample of car battery acid is diluted to a total volume of 50 milliliters with deionized water and mixed with 2 drops of phenolphthalein. So this information here, since I am given information about, okay, I've got an indicator that's present and I have a sample of something that is to be tested, this is probably going to be my analyte. So this is something that I am putting in the flask, something that I want to determine the concentration or aqueous composition of from my stoichiometric analysis of reaction via titration. So I've got my 1 ml sample of car battery acid diluted to a total volume of 50 mils with DI water mixed with 2 drops of phenolphthalein, and the results of the titration with 0.125 NaOH are given below. So I'm going to go ahead and highlight this as being our titrant. So this is what's in the burette. And I am ultimately tasked with finding some information about my analyte, which is specifically what is the composition by mass of the car battery acid with respect to sulfuric acid, meaning car battery acid contains some concentration of sulfuric acid, but the question here is how much? So if I were to give you some raw battery acid, how much of it is sulfuric acid and how much of it is water? How dilute is that sulfuric acid sample in the car battery acid? So this is the ultimate question we're trying to figure out. Something about the quantity of sulfuric acid present in our sample of the car battery acid. So I gave us some information here about car battery acid, like its density. I've also given us some molar mass of sulfuric acid. And now I have the titration results that are given below. So let's kind of look at these titration scenarios. So we have our pre-titration scenario here on the left. So I've got my burette full of my titrant, which remember my titrant is my 0.125 molar NaOH. So that is what's in my burette so far. And down here in my analyte flask, this is where I have 1.00 milliliter of my car battery acid. I've got 49 milliliters of DI water because I was told that I had diluted to a total volume of 50 mils. And then I have 2 drops of phenolphthalein indicator. And you'll notice that when we look at this reaction flask, it is going to be a colorless solution because we have an acid mixed with our phenolphthalein, and phenolphthalein is colorless in acidic environments. All right. Now, after the reaction has happened, so my post-titration, I have now noticed a difference in the height of my NaOH that's in my burette. And the difference between my starting amount of volume read on my burette and the final amount of volume read on my burette is going to be what's added. So let's kind of visualize this, knowing that my titrant, or what's in the beaker, is my what's in the burette, 0.125 molar NaOH. All right, so I'm going to zoom in on this real quick. So it looks like I've got my meniscus here as my starting initial volume. And then looking at my meniscus here, that seems a little low to me. Here, for my final volume, looks like this. So here I have my initial volume reading, and then down here I have my final volume reading. The difference between these two volumes, in other words, this amount of volume encapsulated between these two lines, right? This is the amount of NaOH that was added. So the difference in our volumes, or the difference from final and initial burette reading, gives the volume of our NaOH added. So let's see if we can't figure out what that is. So now I am going to erase these black lines so we can try to do our best and obtain some kind of initial and final reading. So let's zoom in over here on the initial volume. So looking at my volumetric markings, 0, let's see here, 1, 2, 3, 4, this is 5 mils, this is 10 mils, so every marking is 1 milliliter, meaning I can approximate down to 1/10 of a milliliter. To me, this looks like I am not exactly right at my marking there, but just below. So I'm going to approximate this as, let's see here, 1, 2, 3, let's do 3.1 milliliters. And remember, we are always reading our burettes from the 0 line downward. Okay, so that was my initial volume. Let's see if I can't find the meniscus of my final volume. So again, let's see if I can approximate where this meniscus is. So it doesn't look to me like it is quite meeting that blurred line there. It looks a little bit below it. So I'm going to start from, here's my 15 mil line. And if I read going down, for me, this looks like, let's see here, 15, 16, 17. Doesn't look like I'm quite at 18, so maybe 17.8, because it doesn't look like right up against 18. So I would say that my final volume is 17.8 milliliters. And now that I have read my menisci, I can figure out the total volume of NaOH added by taking their difference. So that volume is going to be my 17.8 milliliters, which is my final volume, minus my initial 3.1 milliliters. So if I were to take this difference, that would be 14.7 milliliters of NaOH added. And that is what brought us to this endpoint. So at the endpoint, which is where 14.7 milliliters of our 0.125 molar sodium hydroxide has been added. We see a faint pink color due to the slight basicity or alkalinity of the solution, because we have added just enough of the base to neutralize all of our acid and then a little extra. So let's look at what's going on at equivalence. In other words, let's look at our neutralization reaction. So I'm looking at the reaction of H2SO4 with the sodium hydroxide that I'm added. Neutralizations always form HOH, so I can think about my double displacement. And then I'm going to have left over my sodium and sulfate, so this becomes Na2SO4 in solution. And if I want to make sure this is balanced, I will notice that I have two H's but only one OH here, so I need to double the amount of NaOH. That will then double the amount of water made. And now, if I were to write my net ionic equation, starting with only my complete, I would have two H pluses coming together with one SO4, two Na pluses, and two hydroxides to form two HOH liquids. Everything else is aqueous. Two Na plus and one SO4 2 minus. Sulfates are spectators, the two sodiums are spectators, so my net ionic equation, oh good, this has a 1-to-1 reaction of acid and base. To form two liquid waters. So this is my recipe, this is my net ionic equation. This is going to give me my mole ratios. Okay, so I know a volume of analyte that I added, right? And I know that all of my analyte added, so all of my actual quantity of NaOH that was added has perfectly neutralized at equivalence all of the amount of H, which came from H2SO4, that was present in the sample. So all the sodium hydroxide, titrant added is equal to all of the sulfuric acid that was neutralized in our car battery sample. So let's try to figure out the amount of sodium hydroxide added. So I know the volume of sodium hydroxide added, that was 14.7 milliliters. And I'm trying to get mole quantities here because, again, when I get my balanced chemical equations, I am looking at mole ratios, stoichiometry, mole counting. So if I'm going to try to convert this quantity in volume into moles, the only thing that relates moles and volume is moles per liter or molarity. So I need to first convert this into liters. So there are 1,000 milliliters per 1 liter of NaOH. And then since I am looking at my net ionic equation, I need to ensure that I am looking only at my hydroxide. So let's first figure out how much NaOH was added and then convert that into hydroxide. So let's see here. I added 14.7 milliliters NaOH, and I know that my concentration of NaOH was 0.125 moles NaOH per 1 liter of sodium hydroxide solution. And this is now where I got to be careful, where I need to look at just the hydroxide. So I'm going to use the subscripts in the sodium hydroxide chemical formula to say that for every 1 mole of sodium hydroxide that was added to our flask, we were adding 1 mole of hydroxide ion because each unit of sodium hydroxide carried 1 hydroxide ion. All right. So let's figure out what this is. So I need to take our 14.7 milliliters and convert that into liters. So I'm going to move my decimal over 3 places. So that's 0.0147. Multiply that by my molarity, 0.125. And then multiply by 1, I get 1.83, carrying 7 and 5 for future calculations, times 10 to the negative 123 moles NaOH added. And specifically, this is moles of hydroxide added. All right, now at equivalence, by definition, which is more or less what we're witnessing at the end point, at least in Chem 210, that's okay enough to say, we know that we have added this many amount of hydroxide particles because there were in our original flask this many moles of H+. So at the equivalence point, which is what we observe when we watch the color change at the endpoint, this means that we have 1.83 times 10 to the negative 3 moles of H+ present in the flask. And let's be careful here. What are we ultimately being asked? We are being asked about the percent of H2SO4 in the battery acid. So I don't want just information about the H+ ions, but rather the H2SO4 molecule sulfuric acid. So I have 1.8375 times 10 to the negative 3 moles of H+. And I know that all of those H pluses came from H2SO4. And looking at that subscript, for every 1 mole of H2SO4 that was dissolved, that generated 2 moles of H+ in solution. So I need to divide this mole quantity by 2 to get my mole quantity of sulfuric acid. So let's see here, when I do that, we get 9.18 carrying 7.5 times 10 to the negative 4. Please correct me later if I am incorrect with my moving my zeros over. This is moles of H2SO4. And remember, what we want is the mass percent H2SO4 in our car battery acid. So let's remind ourselves about what the definition of mass percent would be and how we would calculate it for this particular situation. So mass percent, mass of interest, that is the thing that's dissolved in the battery acid or our sulfuric acid. So we want to know the mass of interest over the total mass, which is the thing containing that solute, which is the battery acid. And then to make it a percentage, times 100%. So let's see if we can't get the mass of sulfuric acid. Let's see here, mass of sulfuric acid. Well, I know a mole quantity of sulfuric acid, right? I know that in my flask, I neutralize 9.18 carrying 75 times 10 to the negative 4 moles of sulfuric acid. And since I'm trying to get this into a mass, I'm going to use the conversion that relates moles and mass, in other words, molar mass, where specifically I'm going to need to multiply by my molar mass so that my moles of sulfuric acid will cancel, leaving behind grams sulfuric acid. And I gave us the molar mass way up in the beginning of this problem. I said the molar mass of battery acid is 98.079 grams per mole. So there are 98.079 grams of mass if you had 1 mole of sulfuric acid. So doing this product, this gives me 0.0901 carrying 1008 grams H2SO4. All right, great. I've got my numerator for my mass percent. Now I need to figure out what's going on with my battery acid mass. So I need to think about where all of this sulfuric acid came from. So going back up to either looking at my analyte beaker or what was given in the problem. I know that I had a 1 ml sample of battery acid. That 1 ml sample of the car battery acid is what was the entire source of all of that sulfuric acid. So that's the quantity that I know about my car battery acid. So I know that I had 1.00 milliliter of my battery acid. Now, I do not want a volume of battery acid. I am trying to solve for a mass of battery acid. So let's go back up to the problem. Aha, notice I was given the density of battery acid, which is 1.4 grams per mil. So if I were to set up this unit conversion, I want to get rid of my milliliters of battery acid to be left with grams battery acid, and that was 1.40 grams per 1 mil. So taking 1 and multiplying it by 1.4, this gives me 1.40 grams of battery acid. And now to do my mass percent, I need to figure out their quotients of these two masses and then times by 100. So I have my 0.0901, and then I'm going to use the unrounded value, 1008 grams of sulfuric acid obtained from my mole amount of sulfuric acid from my stoichiometry over my 1.40 grams of battery acid times 100%. Okay, so let's do that quotient, 0.0901. 11008 divided by 1.40. I'm going to be limited to 3 sig figs as I was limited to 3 in the numerator and then also 3 in the denominator. So when I get this times 100%, I get 6.44% H2SO4. This is actually rather dilute. Car battery acid, I believe, should be closer to 60% and not 6. So that's interesting. But yeah, this is what our experimental results tell us, that this is the mass percent of sulfuric acid in the car battery. Okay, this is almost exactly what's going to go on when you do your acetic acid titration. Same idea even with the mass percent, so this is a good example to review for practicing the calculations required for part 2 of our titration of vinegar lab. So that concludes the second part of today's lecture. And then I am actually going to combine these into one last section, and I will post some supplementary material, meaning I'm going to stop talking for you to review about percent yield. We're going to talk about this in future labs as well. And that will be it for today, Wednesday the 12th. So I will see you in lab tomorrow to wrap up our titrations. Have a good one.